Welcome back. We continue in this lecture the justification and process of relaxing the modern rules. We had discussed in earlier lectures that if there is a weak law and they are conflicting with some strong laws, then we can neglect the weak laws and we learn the techniques of doing so. But if none of the conflicting laws can be disregarded, we must abandon the idea of modeling the whole phenomena. Instead, we can try to circumvent the most troubling law by any one of the methods that we discuss today. The first strategy is to restrict the generality of applications. The phenomena is broken up in a number of special cases, each governed by fewer laws than the entire phenomenon. And if enough special cases are investigated, and if they are all relatively independent of each other, an approximation of the total phenomenon can be obtained by superimposing results of these special cases. Let us consider a ship in a severe storm at sea. Since the ship is operating in two distinctly different environments, the air and water, we can test two special cases. First, the ship is in still water but exposed to wind forces. And second, the ship is in still air but exposed to forces of water. Another special case that can be investigated independently of water and wind resistance is the hull's structural response to wave impact. Each of these special cases allows more scaling freedom than is allowed by the phenomenon in its entirety. Let's do in detail an example of modeling of Earth working machines. The soil-machine interaction system is ruled by 6 basic forces. First, the inertia of soil particles. Second, friction between soil particles. Third, cohesive force between soil particles. Fourth, the weight of the soil. Fifth, the elasticity of the soil. And sixth, the adhesion between soil and the machine. Since the soil is being worked to this extreme, and the soil failure takes place in such machine interactions, we may neglect soil elasticity completely, since the displacements are far beyond the limit of soil failure. Similarly, the adhesion between soil and machine can be disregarded by assuming that a thin layer of soil adheres firmly to the contacting machine surface. So any further interaction of soil with this is only with the soil, not with the machine surface. Thus, there are 4 laws that need to be modeled. The inertia of the solid particle is like rho L square V square. The friction between soil particles is modeled by F, the coefficient of friction. The cohesion between soil particles is like C L square, where C is the cohesive coefficient, and the soil weight, which is like rho G L cubed. It is very difficult to choose soils with different values of rho, F and C. They go always as a package. We need to choose the same soil for the model test because of the second requirement above. The F itself is the pi number, and invariance of that would require that the value of F be same. And if the value of F is same, and we can't choose row F and C except as a package. Therefore, the density and cohesivity are also same. This requires that KL be 1. No scaling is possible. Hence, if we want to scale, the relaxations are required. So, let us see how we go about this. One of the methods of taking care of this problem is to classify soils as sandy or clayey. Clay soils are entirely different from sandy soils. Normally, a soil has mixed property, some clayey and some sandy. But let us separate these in two classes. The clay is composed of very small particles having the size of few microns. The internal surface of clay is very large, and surface forces such as cohesive forces are therefore much larger than the gravitational forces. Therefore, the gravity may be neglected. In addition, many clayey soils show very little internal friction. There is largely cohesion, so that F can be disregarded too. So now only the first and the third law need to be modeled. So the same soil requirement can be dropped. We can choose different soils since we no longer need to keep F constant. The first and the third give the modeling rule that C by rho V square is constant. So the modeling rule is C divided by rho V square is constant, and from the third requirement we get the prediction rule that F divided by C L square is a constant. On the other hand, if we deal with the sandy soils are composed of relatively large particles having very little cohesion. Hence, the third requirement can be neglected. Since the inner surface of sand is small as compared to clay, the weight forces are substantial and must be taken into account, along with the internal friction between particles. Therefore, laws number 1, 2, and 4 above apply. From the first and the fourth, we get Froude number, and Froude number requires that KL be like KV square since KG is 1. This is the modeling requirement. We also need the modeling requirement that F be invariant. This requires that we use the same soil. And then we get the prediction rule from the last law, that is the soil weight, and that is F divided by rho L cube is constant for sandy soils. Most natural soils possess characteristics of both clay and sand. That is, they are cohesive as well as there is internal friction. These characteristics cannot be modeled simultaneously, but the special soils of either dry sand or soft clay may be modeled separately because dry sand lacks cohesion and the soft clay lacks internal friction. Hence, by testing the model of an earth-working device first in dry sand and then in soft clay, we can estimate with some confidence its performance in mixed soil. Let us consider the process of bulldozing. Here, the blade of the bulldozer is pressing the soil in that direction with the force F. If we do these experiments, then by changing the length scale KL, this dimension represents a length dimension. So by using different length scales, we determine the force required to move the sand. And in one experiment, we get these results. The slope of the line on log-log plot is 1:2. This indicates that Kf varies like Kl square. And as discussed earlier, this means that this is a sandy soil. In the other experiment, we are considering the vertical penetration of a slab B. As the soil gets compacted, the required force F increases as Z, the penetration distance, increases. So in our experiments, we measure the forces for the various values of B by Z ratios. And in two different experiments, we use the same values of B divided by Z, so that the scale factor for B as well as Z is the same, the KL. And if we determine the force, the variation of force by KL on a log-log plot is with a slope of 1:3. This means that F varies like KL raised to power 3. This we saw is valid for clay soils. So if we do this experiment, we get data for clay soils. How does the force of penetration vary with penetration? Another class of techniques involve simulation of law. And this is a very interesting class of techniques. In vibration and deformation of structures under external loads, as well as their own weight, two laws come into play. Elasticity, the elastic force, is like sigma times A, which is E epsilon L square, where E is the elasticity, epsilon is the strain, and gravity force is like mg or rho L cube g, which gives you KL is equal to KE by K rho, a single pi number, which is K of E by rho. And E by rho is nothing but the wave speed in the material, the speed of the longitudinal waves in the material. So we must keep the length scale as Ka square. A is the wave speed. Now, for metals, the range of speeds, the range of wave speeds is very limited. We compare steel to an exotic material like silver. A square changes by a factor of 3 only. So the maximum value of KL that we can use is 3 if the model is made of silver. Obviously, that is not going to fetch us much returns. So we need to simulate the law of elasticity. This difficulty can be overcome, however, by increasing the weight of the model structure without changing its elastic properties. That is why we use the term dummy weights. This is done with a series of equally and closely spaced dummy weights attached rigidly to the model structure. Thus, to this cantilever beam, we could attach a series of equally and closely spaced dummy weights. Since these dummy weights are all not connected together, they contribute very little to the elastic modulus, but increase the effective density. So, for the model, the density rho can be written as rho naught, the density of the base material, plus delta m by delta v, where delta m is the dummy weight per unit volume of the basic beam. And then a square for the model is nothing but em divided by rho naught plus delta m by delta v for the model. Thus, we are able to change am for the model drastically. There was a bridge, a cable stayed bridge. Several weeks after being open to traffic, the bridge was observed to vibrate vertically in the winds between 40 and 50 kilometers per hour at a frequency of 0.6 hertz. Only in a small window of velocities, 40 to 50 kilometers per hour, the bridge vibrated. And the frequency was about 0.6 hertz. Now, why would the bridge deck vibrate? The deck of the bridge vibrates because of the vortices that are shed from this when the wind blows past this. If I have a rectangular section as shown here, representing the section of the deck of the bridge, as the wind blows past this, a series of vortices are shed. These vortices, when they are shed alternately from top and bottom of the cylinder, cause to apply a vibratory force on the cylinder, a force up and down. And if the frequency of this vortex shedding matches with the natural frequency, the resonant frequency of the bridge deck, the bridge could develop very large vibrations. The frequency of shedding of these vortices is governed by a constant value of the Froude number, Fl by V square. So given a natural frequency of the bridge and the length, that in this case would be the height of the deck of the bridge, so this would be resonant only at a particular velocity, and that velocity is between 40 to 50 kilometers per hour. We need to make modifications to the design of the deck so that the frequency of this changes. After we change the design, we need to test it in a wind tunnel. And one of the method is to use dummy springs. It is very difficult to match the springiness and the mass of the whole bridge. So we take a section of the deck of the bridge, put it inside the cross section of a wind tunnel, and we suspend this model on a set of linear springs outside of the wind tunnel as shown, and the strength of the springs, the spring constants, are adjusted so that they give a frequency which is equal to the natural frequency of the actual deck. And so, with using these dummy springs, we could model the bridge in the wind tunnel. Let us do in some details the modeling of a structural failure experienced by an aircraft carrier. This was an American carrier which broke up in a storm. The ship's behavior is assumed to be governed by inertial forces of the ship and of water, governed by Newton's law of inertia, and by the weight of the ship and the water, and the elastic forces of the ship. Since the propulsion is of no immediate interest, resistance due to the fluid viscosity is neglected. Inertial forces or the law of inertia, F varies like ma, gives us a pi number F divided by rho L square V square in line with similar expressions obtained earlier. The law of gravitation gives a pi number F divided by rho G L cubed. In the elasticity gives a pi number F divided by E epsilon L square, as was done in the previous example of the vibrating beam. Inertia and the gravitational law gives you a pi number as Froude number V divided by under root GL. In the elasticity and inertia gives you Cauchy number rho V square epsilon E. Since K epsilon being non-dimensional itself, K epsilon is treated as 1, so we get KL is equal to KE by K rho. Same as we obtained before. Since the model tests are usually performed in water, K rho is 1. The density being a representative quantity stands not only for the density of water but also for the density of ship structure. The ship's model, therefore, is to be constructed for the material of the density of steel, but with the modulus E vastly smaller than that of steel. Such a material does not exist. So, it is not possible to model the phenomena fully. Therefore, we reduce the scope of the study and restrict the model study to the bending vibrations of the ship. And here we infuse analytical knowledge of the bending vibrations in determining the laws of modeling. The law of bending vibrations are governed by equation that the bending moment M is like EI, bending modulus, into d2y by dl squared. This is moment. So moment varies like EI divided by L. So the force would vary like EI divided by L square. So the relevant pi number is FL square by EI. This is if we consider only the bending vibrations of the beam. So we start with this, and then the Cauchy number becomes rho v square L square divided by EI divided by L square, or L4 rho v square divided by EI. Recall that I varies like L raised to power 4. If the beam of the shape is geometrically similar. So we'll distort the similarity of the beam such that I does not vary like L raised to power 4. If we use the same material, that is, if we use rho and E as the same, K rho and Ke to be 1, then Kv becomes equal to under root Ki divided by Kl raised to power 4. And the Froude number, which requires that Kv be like under root Kl, results in Ki being like Kl raised to power 5. In one study, the selected length scale factor was 136. Therefore, a model had to be built of the same material as the prototype, whose area moment of inertia, that is I, was 136 raised to power 5 times smaller than that of the prototype. Ki was 136 raised to power 5. Such a model was built by composing the hull of 9 segments, all joined by a continuous beam to allow flexures. Thus, the hull of the ship consists of 9 segments, all connected by a beam inside, and the design of the beam was such that the I was scaled as KL raised to power 5. The area moment I of the prototype was calculated by a computer study. The model beam was varied to make it conform to the model rule of I prime. That is, I of the model is equal to I of the prototype divided by 136 raised to power 5. This model was then used to study the ship's vibratory response at regular and irregular seas. Let us consider how to model the performance of an icebreaker. Icebreaker works in generally 2 modes. One is the continuous mode, where the nose of the icebreaker ship penetrates the layer of ice on the sea. And the other method is the ramming mode, which can be divided into 3 phases. The ship impacts and crushes the ice, and it slides upon the ice The weight of the ship now acting on this ice causes the ice to bend and finally to break. The ship again advances, crushes more ice, slides further on the ice, and then breaks the layer of the ice because of its own weight. The ice cracks around the ship. In this process, three forces dominate: the inertial forces of the ship, the gravitational forces of the ship, and the ultimate stress forces of the ice. The ice is breaking. So it is controlled by what is the ultimate stress force of the ice. All other forces, due to the acceleration and submersion of broken ice and to friction and wave making, play only minor roles and can be neglected. The Newton's law of inertia gives a pi number F divided by rho v square L square. The law of gravitation gives pi number F divided by rho L cube G. And the ultimate stress relation gives a pi number F divided by sigma u L square, where sigma u is the ultimate stress of ice. The last two gives a pi number sigma u divided by rho Lg. The model also operates in water so that rho g and sigma u are all same, their scale factors being 1. And so this leads to KL is equal to 1. That is, no scale model is possible. We'll have to work with the full scale model. In situation like this, we infuse some analytical knowledge, and this often proves useful. Here it is assumed that because of the failure of ice is mainly ascribed to its being bent, the ice will follow the theory of flexion. The bending moment is expressed as the bending moment M is the force sigma u L z. We use a different length scale in the vertical direction, in the direction of the thickness of the ice layer. So if the thickness of the ice layer is Z and L is the horizontal length scale, then the area of the ice layer is L times Z. And the moment when we apply, you will determine the moment by multiplying the force with Z. So that the moment M varies like sigma u L Z squared rather than sigma u L cubed if we had used Z is the same scale as L. So the stress relation, the last relation here, changes to F divided by M divided by L, converting moment into force. And so that gives you F divided by sigma u Z square instead of F divided by sigma u L square. And if we use this, the invariant pi numbers become sigma u Z square divided by rho L cubed G. For K, sigma u, K rho, and Kg all equal to 1. That is, if we work with water, this leads to Kz is equal to Kl raised to power 3 by 2. Thus, we can choose any Kl provided we scale the thickness of the lice layer differently according to Kz is equal to Kl raised to power 3 by 2. With Kl is equal to 50, Kz is 354. A much thinner layer of ice then would be dictated by strict geometrical similarity. This is a result that could be easily implemented in the controlled environment of an Arctic pool where the experiments are done. For isotropic homogeneous energy conservative materials, Hooke's law results in two representative relations for epsilon. Epsilon varies as sigma divided by E in the longitudinal direction, and epsilon varies like nu, the Poisson ratio, times sigma divided by E in the transverse direction. It is obvious that geometrical similarity between the model and the prototype can be satisfied only if either the same material is used so that E and nu have the same values in the model and the prototype, or different materials are used with different moduli for elasticity but still the same Poisson's ratio. These requirements again suggest use of the same material for model and prototype. The condition of same material can be relaxed only if the transverse deformations are disregarded. Then the influence of Poisson's ratio becomes unsubstantial and permits the use of different materials for model and prototype. This disregard of Poisson's ratio is an important relaxation in almost all structural problems. Thank you.